weight 3, d to f of weight 6, and e to f of weight 2. Okay, so we have this graph. So you could think of representing a graph in terms of its edges. So A, B, 4 means the vertices in the edge are A and B, and it has weight 4. And then A, C, 2 are, it's another edge. A, E, 3 is another one. B, E, 5 is another one. C, D, 1. C, E, 6, C, F 3, D, F 6, E, F 2. So one way you can kind of store the graph is like as these tuples, where the first two coordinates represent the two vertices in the edge, and the third coordinate represents the weight. So it's relatively simple data structure. Now, if you want to do Kruskal's algorithm, then you have to sort these. So 1 is the smallest one, then 2. Then 3. Then we have a 4, yeah. And we have a 5. And we have 2 6s. So we can sort it. List it this way. So, following the Kruskal algorithm, again, the idea is that you go through the sorted list and you draw the edge unless it forms a cycle. So if you're just drawing it, it's kind of easy to see if it forms a cycle, but maybe we can build a data structure where it's easy to find out if a cycle is created or not. So in the notes, they suggest creating a data structure called the disjoint set data structure. So this is a collection of disjoint sets, and each set is named by one of its members. And so I guess you can create a class called disjoint set and then have a few functions in there. So one of them is makeSet, which creates the set that just includes the letter X. Another function is findX, which tells you what the set that contains X contains. And union XY gets together two sets that contain X and Y. So it's a data structure you can build. So how does it look under this data structure? So the first step is you make sets I guess A, B, C, D, E, and F. So you make these sets. You're thinking of writing the Kruskal algorithm, then step 1 is for each vertex in the graph, you create the singleton set. So now you're going to read down from the sorted list of edges. You see this guy, and you get these two together. So you do the union of those. So, if the two vertices of an edge already belong to the same set, then you can't put them together because you would form a cycle. So this union was legal because C and D are disjoint. You create that. So you use this, then you do AC2. So that's, these two create that set. That's also legal because the union built a new term in there. So there's no cycle. So you use this, and then EF2. So now so EF2 creates the set here. EF. So when you use this, it creates that set. And then when you do AE, then you get this together with that. They're still disjoint. So when you take your union, you get that. And then when you think of CF, they're already in the same set. So this one would form a cycle. When you do AB, they're not in the same set. And you're done. Of course, by hand, this is pretty easy. You do AB, AC, EF, AE, and then CF would form this cycle. So you get CF, AB. Oh, I guess I drew AB too early, sorry. It was CD. CD was first, then AC, then EF, then AE. And if you tried CF, you would get a cycle. Then you do AB, and now it's a spanning tree because all vertices are connected, right? So if you use this data structure, you know you end when at the end you just have the set where everything is connected. So here in the notes you can see at the first, before you draw the first edge, the disjoint sets are A, B, C, D, F. Once you draw C and D, then now you have 5 disjoint sets, A, B, C, D, E, and F. And once you draw AC, now you have 4 disjoint sets. This is one of them. So the ACD, B, E, and F are the others. When you draw EF, now you're left with 3 disjoint sets. When you draw AE, you're left with 2 disjoint sets. When you try to do CF, you can't, and then when you do AB. So this, if you create this data structure, it's pretty straightforward to do the algorithm. Okay, so one annoying thing could be like, well, how do we know that CF, they're both in the same set? So when you try CF here, you see that find C equals find F. So remember, find an element tells you the set that includes that element. So because they're equal, that's why this is why you skip this edge. But what is, well, anyway, doing this find business might be time consuming, right? If you want to if you're checking each time how big the set that contains X is, you might be doing loops through the whole thing. So it's a quadratic behavior. So then an efficient way to represent these joint sets is to use trees. So if you keep track of them as trees, then it's a little easier to find things, because then you can just keep including the parents of the things and keep including the children. And then that way you build this A, B, C, D, F quicker for C. That's kind of the idea. So you're trying, well actually, that's not even the best way. The best way is you can just follow the path to get to the root. So like, suppose here you have some tree that was built from this. So A and C are linked, and then, sorry, C and D are linked. Let's put C on top. And then A is attached to those. And E and F are connected over here. And what did we connect? Sorry, I guess. So C and D are connected, then A and C. So you could put A as a child or as a parent. Let's do child. And then E and F are connected, and then we have A and E, so this gets glued in there. Right? So when you do find C, you could, instead of generating the whole set, you could just be like, let's find its parent. So if you do find C, it would give you this. And if you do find F, you just follow through and you also get this C. And if they both have the same root, then they must be the same set. And you would create a cycle. So that's kind of an idea you can do to speed up some of these steps in the disjoint set data structure. So instead of having to loop through everything, you can store them as they go as a tree, and then when you do the find C, it just, instead of returning the whole set, maybe you create it so that it returns the root of the tree. And if two things have the same root, then they must be the same tree. That's the and then it has how would you code these? The nodes have it, they're pretty straightforward. So how do you merge two roots? How do you merge a find set, etc. Alright, so this is how you can implement the Kruskal technique. If you do some other clever ideas, the running time of all of this is number of edges times the logarithm of the number of vertices. If you then do some trick called path compression, you can get that the running time is number of vertices plus number of edges. So, you know, this beats quadratic behavior. Whatever technique you use to implement Kruskal, the main goal is you should care more about the number of edges than the number of vertices. So, number of edges tend to be a lot more than the number of vertices. So, if you had like v times log v plus e, that would still be better than E times log P. Okay. Any questions on Kruskal's algorithm? So for midterm 3, you have to be able to do Kruskal by hand and also Prim's algorithm by hand.
Delightful.
All right. Let's see. So the next important algorithm is Dijkstra's algorithm. Let's get to that. Alright, so this Kruskal and Prim, the goal was to find spanning trees of graphs. So there's another concept that's important that are directed graphs. So in a graph, the things are connected and it works in both directions. So you could think of that like most roads are, you can drive them in both directions, right? But some things, the direction you're traveling in matters. Actually, even in roads, it matters. But if you look, say, at prices for flights, if you're going from Chicago to Washington, the price might not be the same as if you're going from Washington to Chicago, right? So it's not just, you can't think of it as just one edge connecting the two cities, Chicago to Washington. You actually have to think of it as one going from one to the other, having some weight, and another arrow in the other direction. So a directed graph it's like the direction you're going to matters. Alright? So sometimes they're called digraphs. Just digraph. I think it's more common to see a directed graph, but these notes from this free book I linked to for you is they use digraph every now and then, so just pointing out what it means. So a directed graph the edges have a direction. So, and a weighted directed graph is where the directed edges have weights. Okay? Okay, so I know we've been using weights for calling these things in Kruskal's algorithm and Prim's algorithm, but for historical reasons, for Dijkstra's algorithm, they prefer now thinking of them as lengths instead of weights. I mean, it's the same thing. That they have a value associated to them. You can think of it as weight, as length, as distance, whatever. So one thing you could care about is you have some graph. And maybe you have some lengths here. Anyways, you have a bunch of arrows in all kinds of directions. Each one has a number associated to it. And one thing you might care about is what's the shortest path from a vertex to another vertex. To U to B. Alright, so we care about this question. If you start in one vertex and you're going to another vertex, what's the shortest path? Okay? So let's just think of some baby examples. Maybe you have like A, B, C. Let's say you have this graph. Well, I guess this one isn't connected yet. So let's add that arrow, and let's put some numbers. Let's say this is 3, this is 4, and then this one is, I don't know, 10, and this distance is 5. Okay, so if we write it in the notation, the other one, we have an edge from A to C with weight 3, we have an edge from C to B with weight 4, we have an edge from B to A with weight 5, and we have an edge from A to B with weight 10. Right? So that's a directed graph. It is connected. You can get from any vertex to any other. If you want to get from A to B, you can just use this guy, or you could follow A to C, C to B. If you want to get from B to A, you can go from B to A. If you want to go from C to A, then you can travel to B and then go up to A. So for any two vertices, there's a way to go from one to the other. It's a connected, directed graph. So now, what are the shortest paths? So I'll call, did I use W or distance? Alright, so we'll just call it the distance between two vertices. So from A to B, you have two possibilities. So to get from A to B, you could either go from A to C, and then from C to B, or you could just go straight from A to B. If you do this path, the cost is 7. If you do that path, the cost is 10. So the best way to go from A to B in terms of cost would be go to C and then go to B. So you have 3 plus 4, it's less than 10. So the distance from A to B is that 7. The distance is defined as the shortest path from one vertex to another. So now if you want the distance from A to C, then I think the only, Well, there's many ways to go from A to C. You could go from A to C, or you could go A, C, B, A, C. You could just keep looping around, right? So the distance from A to C is just 3. That's easy. The distance from B to A is 5. I doubt that you can beat just going straight. The distance from B to C so you have to go to A and then down to C. So that's 5 plus 3 equals 8. The distance from C to A. So from C to A, you have to go B and then up to A.
I'm stupid.
And the distance from C to B is 4. Okay? So you can find all these distances. Alright, so sometimes, this is a very small graph, so it's kind of easy to just analyze all the possibilities. But even in this small graph, when we were thinking of the distance from A to B, there's actually 2 possibilities to consider, and we have to take the minimum of those. So when the graph is more complicated, it has a bunch of vertices, a bunch of edges, and you want to know the distance from one vertex to another, then analyzing all the possibilities is too much work. So there's an algorithm called Dijkstra's algorithm. And all right, so here's the algorithm. So you have a directed graph. Well, let's see what the conditions are. Okay, yeah. All right, so here, if you think of the weights, so from A to B, the weight is 10. From A to C, the weight is 3. From C to B, the weight is 4. From B to A, the weight is 5. All right, so these are weights that are given to us from the graph. However, there's some edges that don't exist. So for example, there's no edge between C and A. So when there's no edge, we're going to define the weight to be infinity. There's no weight between, so there's no C to A, there's no B to C. Those are the only ones that are not there, right? So to be able to implement Dijkstra's algorithm, you add these infinity values to any directed edge that doesn't exist there. Alright, so the algorithm is, let n be the number of vertices. So you have a sequence. All right. So maybe let's add more things here. So you have your number of vertices is n, and then you first do step 1. Oh yeah, so we want, let's see, what is this solving? Path from R to X, all right. So it's going to be the shortest distance. From R to X. All right, so step 1 is you have sigma is just your R. So this will be your permanent vertex, and the rest are temporary vertices. All right, so we let delta r be 0. PR is a one-point path. So I guess the P will be the path, the deltas will be like the distances. And I guess sigma is for sequence. Okay. Now for each x in V, we're gonna let delta of x be the weight from R to X, and Px will be the path Rx. Right, so let's work with these guys. So I have okay, so we have those numbers, right? At the first stage, we have we're trying to, let's say R is A for us. We're just going to go from A to the other guys. So then we're going to have that there are several paths depending on X, but we're going to determine that these distances are, so from A to C is 3, from A to B is 10. Okay, so in this case, it's not too exciting yet because no infinities have appeared. All right, so these are your two weights. So the one that minimizes it is from A to C, that's 3, right? So the path says pick the one for which delta x is minimal. So that would be C. So x will be C, because delta C is 3. That's the minimum. So now, I'm sorry, I guess I'll make it. So these are the, I'll put this in dots to symbolize that it was a candidate that it was not taken. So P of X will be AC, basically. All right, so now our sigma will also be AC. So we appended C to A. And then we do the next step. So now our sigma, instead of just being R, is R. Instead of just being A, it's going to be A and C. So we're going to look at all the things that are connected to this. So we have A to C that's a 3. And in this case, there's only one other guy. So you have to consider these things. And you're going to consider the minimum of delta x plus that. So let's see. So this is for any a. So for any x that's not A or C, that the only one is B, so you consider delta B to be the minimum of delta 3 and delta right before it. So that would be, sorry, this is delta C plus the weight from C to B. It's the minimum of 10 and 3 plus 4, which is 7. Right, so the weight from A to B is just 10. But if you're here, then getting to B is 3 plus 4, and that's 7. So that one wins. This particular case was a little easier just because if you start with A as the group, there's no infinites. But so this is the iteration you're doing. So you're building up a path, and each time you add a vertex to it. In this case, you also have to analyze whether you add the vertex or not. Alright, so this is kind of funny, right? You have delta x equals min of delta x and blah blah. So what does this mean? If the minimum happened at delta x, then the path is just r to x. If the minimum happened over here, then the path is the steps you had, and then you add a comma x at the end. Right, so if you were doing, say, the distance from A to C, then once you have this, that's good enough. So you have to iterate this for the number of vertices. Right. So that path sometimes is strange. The path is sometimes like R. There can be repeats. But we'll do a bigger example next class. So Dijkstra's algorithm is a pretty important one. This is one of the things that sometimes comes up in like job interviews. So it's one of those algorithms that you really want to understand well. But we'll spend more time on it on Friday to make sure we know what's going on. An announcement, there is a talk on Monday. So Monday in Brown 251. Or is it 254? So it's the one that's like at the corner in the second floor. 254. 254. All right. So there will be a talk. So this is a grad student at University of Chicago, and she will give a talk of applying trees like this data structures to some stuff. I'll give you more details by email. But this talk will be count as part of the participation grade. Alright, so if you can't make it to the talk, you have to have a good excuse and you tell me what that excuse is, but it's...
What time is it?
Oh yeah, it's 4 p.m.
I can't do that.
You might start 4:10 to 4, something like that, 4 to 5. So again, like those talks that are part of the participation grade, if you can make them, you have to email me and say, oh, I work, or blah blah blah. So you have to tell me why. All right. Okay. I'll see you on Friday then.